Hello and welcome back to our continued journey of trying to master geometry. And our today's agenda is going to be the perpendicular bisector, specifically the perpendicular bisector for various sides of a triangle. So start the story as usual with simply drawing a triangle and trying to understand what a perpendicular bisector is, because the theorems, the deductions, everything will come from that definition. So consider any of the sides, let's say side BC, and find the midpoint of BC. And now any line passing through this point will be the bisector for the line BC. So if I think of this line is a bisector for BC because it is dividing the line BC into two equal parts. So will be this line. And so many other lines you can draw from this point. All of them will be bisectors of the line BC. But we are specifically interested in the perpendicular bisector. That means whatever line I am thinking of passing through the midpoint is going to create a 90-degree angle with the side. So this is the perpendicular bisector. And I can do it from, let's say, one more side, and I do it on this side, find the midpoint and create a 90-degree angle. And now once again, and I'm saying once again because before starting with perpendicular bisectors, I'm assuming if you have followed the order, you have looked at the study of incenters and you've looked at the study of the centroid or the medians. Incenter is nothing but where the angle bisectors meet. So think of another triangle quickly, just a quick recap, a very small revision. These are the angles. This is the angle bisector dividing the given angle in two equal parts. And where all three of them meet or two of them meet was known as the incenter. So not only the definition, now we also have a lot of properties around the incenter, but the definition of, or the term incenter means that from this point you can draw a circle inside the triangle which will touch all three sides. What that means is that if you think of a triangle and if you're thinking of the incenter, the perpendicular dropped from the point to the side, the perpendicular dropped from the point to the side is going to be equal. That means this point is equidistant from all three sides. And how do I measure the distance of a point from a line? The distance is known as the perpendicular distance from the line to the point. That means if I wanted to find the distance, this is the distance, and that's why I put in a perpendicular or 90-degree. And because there is a circle, that means this is the radius, this is the radius, this as well is the radius. So this was the definition of incenter, and incenter meant, mathematically it meant that this point is equidistant from all three sides. And then we looked at a lot of properties related to this idea and derived all of them and understood them well. So I want to do the same thing here. I have two perpendicular bisectors meeting at this point, and this point will be known as the circumcenter. And what that means is that from this point you can create a circle so which will pass through all the vertices A, B and C. What that means is, this doesn't look like a circle, it looks more like an apple. So fix the design in your notebooks. What that means is that if you're thinking of a circle, all points of the circle are equidistant from this point. That means this point is going to be the same distance from A and from C. So that the reason I'm throwing both of them together is so that we can understand this idea of this point being a certain distance from either the side or the vertex, right? In the case of incenter, this point was equidistant from all three sides, and therefore you could draw a circle connecting all three sides. In this case, this point is equidistant from all the three vertices, and you have 3 points equidistant from a given point, and if basic circle theory says you can create a circle so. So that is the meaning of the term circumcenter. But again, my question is why? I can create a circle very easily if I know all these 3 points are equidistant from each other. All these 3 points are equidistant from this given point known as the circumcenter. But why are these two distances equal? y is our obviously the first challenge. So let's try and work on that. So create a general form triangle for yourself and drop the perpendicular bisector. Find the approximate midpoint and drop the perpendicular bisector. Find the midpoint and drop the perpendicular bisector, and let's say they meet at this point. So what I want to prove is, and let me call this point C for circumcenter, and for a minute let me call this point X. What I want to prove is that AX is the same as BX, because if I can prove that, that means that this point is equidistant from this point and this point, and then I will repeat the process on the other side of the triangle and find maybe that this point is also equidistant from this. That means all of these distances are going to be equal to each other. So let's start thinking about that. What information do I have? I know this is 90 degrees, and this, if I call this point P, AP is equal to PB. I know this much information. So now if I think of triangle APX and triangle BPX, they are going to be congruent. Why? There is something known as RHS congruence. If I look at these two triangles, both of them have a 90-degree angle. And if I look at these two triangles, both of them have a 90-degree angle, and this side is equal to this side, so they have a corresponding side equal to each other. And this side is common to both of them. That means they have the same measure. That means I have two triangles where there is a right angle triangle and two sides are equal to each other. In fact, in this case, you have a side angle side congruence also. So in case either which way, you have proved that these two triangles are congruent to each other. That means the side BX is going to be equal to X. Corresponding sides will be equal. So BX is equal to AX. Draw the same story here. There is a perpendicular bisector and say it is passing through this point. We'll question that point also and repeat the same story. Again, two triangles created. I know this is equal to this. Why? Because this is a perpendicular bisector. That means this part is equal to this part. This is common. The 90 degree is common. Once again, these two triangles are congruent, meaning this side is equal to this side. So now you know that this point is the circumcenter. Why? Because it is equidistant from all 3 points, and equidistance means that you can quickly create a circle around it. So staying with the same story and the same curiosity, I know that if I have a triangle and if I create a perpendicular bisector and create another perpendicular bisector, two of them will definitely intersect. Think of this line going somewhere, think of this going somewhere, they will definitely meet. But what about the third side? Why is the third side also coming here? But why is the third perpendicular bisector also coming to this point? So this is a line of inquiry that we have done both with angle bisectors as well as the median. Two of them will meet. Why will the third one meet there? Definitely. And as you have seen, it will have to do with congruence or similarity or even more basic tools that you have learned earlier. So let's get cracking with the problem. What that means is, say I take the side AC and I divide it into two equal parts. And I say, okay, let me connect these 2 points. So I've taken the midpoint of the side and connected to this point X. So my one challenge is proving why is this angle 90, why is this angle 90 degree, or if it is 90 degrees at all. So how will we go about doing that? So what I'll do is I'll connect A to X and X to C, and I know if I call this point P, AP is equal to PC. And if I notice these two triangles, one side is equal to the other side, this side is common to both the triangles, and I just figured out that this point was equidistant from the two other vertices. That means this part is equal to this part, so they are also equal. That means if I think of these two triangles, they are congruent to each other. That means all corresponding sides are equal and all corresponding angles are equal. That means if this angle is X, this angle is also X. And you know 2X is going to give you 180 degree because we are thinking of a straight line. So X is going to be 90 degrees and hence proven. So this is one direction. And again I want to get back to the same problem very quickly. and change my tack and say this is the triangle, perpendicular bisectors meet somewhere, and this time from this point I drop a perpendicular. That means I don't know whether these two paths are equal to each other or not, but from this point I have dropped a perpendicular. Let's see if we can conclude that AP is going to be equal to PC. The story is going to be the same. Let me try and connect AX and XC and see what happens. I know AX is equal to XC. I know this is a common side between these two triangles. So I have two sides equal to each other and I have a right angle. That means I can use the RHS congruence, which tells me that if I have one right angle and two other given sides, I can conclude that these two triangles are going to be congruent to each other. That means all corresponding sides are equal. That means AP is equal to PC. Therefore proven that this is not only the perpendicular, it is the perpendicular bisector. So this is my starting point. Now I know the three perpendicular bisectors meet somewhere. That point is known as the circumcenter. That means I can draw a circle around the three vertices. Why is that? Because that point where the perpendicular bisectors meet is equidistant from all the three vertices, which is the reason for the circle. And now I have also understood that why all three of them meet at the same point. And as bonus activity, I have also revised congruence a couple of times. Before going any further, just to change the diagram slightly so that we can understand that the circumcenter could be outside the triangle also. So say I have this side, somewhere here would be the perpendicular bisector. So my perpendicular bisector will go like this. For this side, my perpendicular bisector will be somewhere here and the perpendicular bisector will go like this. So this is where they are meeting. But it doesn't make any difference. This point is still going to be equidistant from all the three vertices, therefore working like a radius, and therefore you will be able to create a circle around the 3 points. So with the in center, the point was always inside the triangle. With the perpendicular bisector, that is not necessarily true. You might have a circumcenter which is lying outside of the triangle, so be aware of that. So before going further and deeper, another very basic property and a very common property and a well-known property is that where the perpendicular bisectors meet, right, if this triangle is ABC and they meet at this point X, this angle BXC is going to be twice of angle A, and the result of proving this or understanding this is very easy if you have understood circles and basics of circles. This is a circle and this is the center of the circle, and you have learned that in any story the angle dropped at the center is twice the angle dropped anywhere else in the circle. So this angle is going to be twice all of these other angles, which a bonus theorem is also that all of these angles are equal to each other. So a very basic idea from the theory of circles, and just using that, because this is a circle, this is the center of the circle, the angle created at the center is going to be twice the angle is going to be twice as much as any other angle anywhere else in the same segment of the circle. So these are in the same segment, this is at the center, this is going to be twice as much as this, or this is going to be half as much as this. So if this angle was given as 60 degrees, you can say this angle is going to be 120 degrees. If this angle was given as 80 degrees, you can surely say that this angle is going to be 40 degrees. So another key property related to perpendicular bisectors. So I'm guessing fairly easy so far using all the things that we have learned earlier. Now we want to move towards connecting the circumradius to the area of the triangle. But before we can do that, I will need to introduce a couple of other tools and formulas. So let's see, and very easy ones. So let's see how they work and understand them well. So not only we will learn about the perpendicular bisector, the circumradius and the area, we will get to learn a new formula altogether. So for that I am just dipping a little bit into very basic trigonometry. And just by hearing trigonometry, don't reject the idea, because the idea is very straightforward. We will tackle trigonometry in all its detail and glory later, but a very simple idea. Say if I am talking about this angle as a reference, say I say this angle is theta, and I will introduce a term or a ratio known as sine theta, which is nothing but the opposite side divided by the longest side. So say if this triangle was ABC, this side is A, this side is C, this side is B. Sine theta is going to be C upon B. So very easy idea. No more than this is required for our current purposes. There is a ratio known as sine theta, and the very definition of the ratio is C upon B. So that is one idea. Because from here you can go into cos theta, tan theta, properties of theta, further properties of this relationship, and start playing with that. That will become trigonometry in all its detail. But as of now, what is sine theta? For such a triangle, theta is C upon B. And if I consider the area of this triangle, it is going to be half base into the height, which is C. So C. Instead of C, can I not write sine theta into B? Instead of C, can I not write sine theta into B? And there you have it. You have a new formula for the area. Half A into B into sine theta. And if you think of the relationship, this is the angle theta. B and A are the sides making up the angle theta. B and A are the sides creating the angle theta. So you have another formula for the area of a triangle using a particular angle and the two sides creating it. So if you can find sine theta, you can find the area of this triangle. So that's the basic idea. But even as of now, we are thinking of a right angle triangle. This formula can work for any form triangle. So say I have this triangle A, B, C. This is A, this side is B, this side is C. I want to find the area of this triangle. So I will do half base is A, and now I want the altitude. So I want to figure out this side, and let me focus on this triangle AB point. Call this point D for a second. Triangle ABD, and let me call this theta or angle B. Don't even call it theta, call it angle B. And this is a right angle triangle. So if I say what is sine B, what is sine B, you will say the side opposite divided by C. You will say the side opposite divided by the longest side. The longest side is C in this case, the hypotenuse. So sine B is going to be AD upon C. For your area formula, you need AD, half base into height. Your height is AD, but AD can be rewritten as C sine B. So A into C sine B. That means B is the angle, and we are talking about A into C. A and C are the sides creating the triangle. So not only the right angle triangle formula, this formula will work anywhere for any triangle if you start thinking from the angle point of view. So not only we are going towards connecting the circumradius and the area, now have a new unique formula for the area of triangle. So when we get into area of triangle discussion and problem solving, and when I say okay, we have another formula for the area, half A into B into sine theta, we already have the proof, hopefully. So this is one part of the journey of trying to understand the relationship. Now let's look at the next part. And now getting back to our standard story, back to the perpendicular bisector. So I have a perpendicular bisector, I have another perpendicular bisector, so all of these angles are 90 degrees. And I have yet another perpendicular bisector, so if this whole side was A, this part is going to be A by 2, this part is going to be A by 2. If this whole side is C, this part is going to be C by 2, this part is going to be C by 2, and here So we are thinking of the area, start creating smaller triangles, which when added together will create the big triangle. And this was your circumcenter, call it x for a second. This point is equidistant from all three sides, and this is the radius of the big circle. So this is the circumradius, mark it with capital R. This is also capital R. And let me call this point P for a second. And if I notice the triangle BXP and the triangle CXP, R is equal to R. So the one side of both the, so I have one side equal to the other side of two triangles. I know A by 2 is also equal to A by 2, so I have this side as equal as well. And this is a common side. That means S, congruence kicks in. These two triangles are congruent to each other. All corresponding paths are going to be equal to each other. That means this angle is going to be equal to this angle. And we just learned a minute back that this angle is nothing but twice of angle A. That means each of these smaller angles is equal to angle A. This also is equal to angle A. Now I want to zoom into this triangle. Let me draw it out again. It's a right angle triangle. This is 90 degrees. This is R. I don't know this. This is A by 2. And I'm calling this as angle A. So if I think of sine A now, sine of angle A, it is going to be the side opposite, which is A by 2, divided by the longest side, which is the hypotenuse, in this case R. So I get sine A is equal to A upon 2R. And just arranged as a little, you get 2R is equal to A upon sine A. Just the way you have worked it out for angle A, you can do the same proof for B, B upon sine B, and C upon sine C. All of them are going to be equal to 2R. So write this down somewhere, another important result or a rule for you which can come in handy sometime. And it will be immediately used to connect still way, because you're still trying to connect the circumradius to the area. So capture this information somewhere. And now if I think of the area of this triangle, so I will say, okay, let me think of angle A, and I will use what the formula that I just created, half the sides which make up the angle C and B, that means B into C into sine A. That is the area of the triangle, the formula that we just looked at and derived and understood. So the area of this triangle is half into B into C into sine A. And I just saw sine A is equal to A upon 2R. So instead of this, I will write A upon 2R. So what you get is A into B into C divided by 4R. So this is your final connection that we want and wanted to establish and will be using in future problem solving, that if you want to connect the area to the circumradius, this is the case, area is going to be A into B into C upon 4R. Now you will not use this formula to figure out the area of a triangle, but you will use this formula often to figure out the circumradius, because the area you will figure out using half base into height or the Heron's formula or whatever method, or maybe the area will be given or the area will be half of another figure. So whatever way you figure out the area, you using this particular connection, you can figure out the circumradius. So repeat the result a couple of times, maybe hit pause, stop the video, try and prove this for yourself and look at the pieces that are needed. One is the area formula, that you have half, and say if I'm talking about angle B, so I will use C and A sine B. If I'm thinking of angle A, I will say half C and B, C into B into sine A, and so on and so forth. Rest was basic congruence, properties of triangles, etc. In fact, this result that these two angles are equal to each other, if you have gone through isosceles triangles while looking at congruence, you know that if these two sides are equal to each other, if you drop a perpendicular, it works like an angle bisector anyway. So you did not need to prove the congruence, you could have just used the property and said these two angles are going to be equal to each other, and this big angle is equal to twice of this angle. Why is that? Because of the circle properties. angle at the center and angle anywhere else in the same segment, right? So I hope by now you have understood the formula and also understood where it is coming from. So one last property to do with perpendicular bisectors, and even more specifically connecting it to the right angle triangle. So the theory is, which we'll prove in a minute, that if D is the midpoint of AC, which is the hypotenuse, AD is equal to DC, this point is also the circumcenter. That means once I draw a circle around these 3 points, that means once I circumscribe a circle around the triangle passing through all the vertices, this point is going to be center of such a circle. But before we can prove that, and in fact understanding that idea will be the proof very quickly, we will connect it to the idea that we've been discussing already, that if I think of an arc of a circle or a chord of a circle subtending an angle at the center, this angle is twice this angle. So if this is x and this is y, y is equal to 2x. Why is that? We have covered that in the video on circles in quite a lot of detail. So this angle is equal to twice of this angle. That means the angle at the center is twice the angle subtended anywhere else. And if I make it so, and if I think of, let's say, half the circle and the diameter passing through the circle, this angle is 180 degrees. And I'm left with half the circle. That means any angle that I create in half the circle is always going to be 90 degrees. Why is that? Because this angle is going to be half of this angle. This angle, because this is a diameter, is already locked in at 180 degrees. So any other angle in the semicircle is always going to be 90 degrees. And that's it. If you understand this idea, you will understand this very quickly. You have a circle passing through and you have a 90-degree angle. That will make this the diameter of the story, and the midpoint of the diameter will become the midpoint of the hypotenuse. So the hypotenuse becomes the diameter, and this is your circumcenter of. So this is what is unique about the right angle triangle, that once you circumscribe a circle around it, the center is going to fall at the midpoint of the perpendicular. That means if you draw a perpendicular and if you draw a perpendicular bisector from here, they will meet at the midpoint of the hypotenuse. So I think this much proof should be enough of why the center in case of a right angle triangle for the circumscribed circle falls at the midpoint, and the connection is with the properties of circles. So that should be easy. The other interesting result to notice is that if I connect BD, because this is the center of the circle, makes this the radius, this is the big capital circumradius, this is also the circumradius, and this point, the distance from the vertex once again is the circumradius. So BD is equal to AD is equal to DC. So that is another property that you can look at, that if you're thinking of a right angle triangle and you create a perpendicular bisector around the hypotenuse, it will pass through the opposite vertex.